Galileo Galilei is one of the most iconic figures in the history of science, often hailed as the father of modern science. His groundbreaking contributions to physics, astronomy, and the scientific method laid the foundation for modern empirical research. Born during the height of the Renaissance, Galileo's life and work epitomized the transformative power of curiosity and critical thinking. This chapter sets the stage for exploring his extraordinary journey, achievements, and enduring influence. The Renaissance, a period of intellectual rebirth, was the ideal backdrop for Galileo's genius. This era, characterized by a rediscovery of classical knowledge and an emphasis on human potential, fostered a fertile ground for innovation. However, it was also an age where science often collided with tradition and religious orthodoxy. Galileo's life was shaped by this duality. On one hand, he was celebrated for his ingenuity, and on the other, he faced fierce opposition for challenging established beliefs. Galileo's scientific achievements are unparalleled in scope and significance. From refining the telescope to observing celestial phenomena that confirmed the Copernican model, his work revolutionized humanity's understanding of the universe. He was not merely an observer, but also a thinker who questioned the nature of reality itself. By integrating mathematics with experimentation, Galileo moved science away from abstract theorizing toward empirical evidence, setting a precedent for future generations. Despite his monumental contributions, Galileo's life was fraught with controversy. His support for the heliocentric model, which posited that the Earth revolved around the Sun, placed him at odds with the Catholic Church. This conflict culminated in a dramatic trial by the Inquisition, which serves as a sobering reminder of the tension between innovation and authority. Galileo's recantation under pressure highlights the risks faced by those who dare to challenge the status quo. Galileo's influence extended beyond his scientific discoveries. He was a pioneer in developing the scientific method, a systematic approach to inquiry based on observation, experimentation, and analysis. This methodology remains a cornerstone of modern science, emphasizing the importance of evidence over dogma. Galileo's insistence on questioning established ideas inspired thinkers like Isaac Newton, who built upon his work to formulate the laws of motion and universal gravitation. Moreover, Galileo's legacy transcends the boundaries of science. His life story is a testament to the power of intellectual courage and resilience. He demonstrated that progress often requires challenging deeply entrenched beliefs and enduring personal sacrifices. In doing so, he became a symbol of the human spirit's relentless pursuit of truth. Understanding Galileo's life requires an appreciation of the historical and cultural forces that shaped his work. The Renaissance was a period of unprecedented creativity and exploration, but it was also constrained by the dominance of religious institutions. Galileo navigated this complex landscape with remarkable skill, balancing his revolutionary ideas with a keen awareness of the risks they entailed. His ability to thrive in such a challenging environment underscores his exceptional intellect and determination. Galileo's work also marked a turning point in humanity's relationship with the cosmos. Before him, the universe was often viewed through the lens of religious doctrine or mystical speculation. His telescopic observations shattered these preconceptions, revealing a dynamic and complex celestial order. This paradigm shift not only altered our understanding of the universe, but also redefined humanity's place within it. Today, Galileo is celebrated as a visionary who bridged the gap between ancient philosophy and modern science. His contributions resonate across disciplines, from physics and astronomy to philosophy and education. He serves as a reminder that the pursuit of knowledge is a universal endeavor, transcending the barriers of time and culture. In conclusion, Galileo Galilei's life and legacy embody the transformative power of science and reason. His unwavering commitment to truth, even in the face of adversity, continues to inspire generations of thinkers and innovators. As we delve deeper into his story, we uncover the profound impact of his work on our understanding of the natural world and the enduring importance of questioning, exploring, and learning. Galileo Galilei was born on February 15, 1564 in Pisa, Italy, into a family that valued learning and the arts. His father, Vincenzo Galilei, was a prominent musician and music theorist who emphasized the importance of critical thinking and intellectual independence. This environment undoubtedly shaped young Galileo's inquisitive nature and set the stage for his future contributions to science and philosophy. However, like many great thinkers of his time, his path to greatness was neither linear nor without obstacles. In his early years, Galileo exhibited a keen interest in the world around him. He was fascinated by the natural phenomena he observed, often questioning their causes. Despite his evident intellectual potential, Galileo's initial educational trajectory was not oriented towards science. At the age of 10, he was sent to a monastery school in Vallombrosa, where he was introduced to the humanities and religious studies. This early exposure to classical education instilled in him a lifelong appreciation for logic and rhetoric. Galileo's formal education took a significant turn when he enrolled at the University of Pisa in 1581 to study medicine. His father encouraged this decision, as a career in medicine promised financial stability and prestige. However, Galileo quickly realized that his true passion lay not in healing the human body, but in understanding the principles that govern the natural world. His interest in mathematics and physics soon eclipsed his medical studies, and he began attending lectures on these subjects, much to his father's dismay. A pivotal moment in Galileo's early life occurred when he observed a swinging chandelier in a cathedral. This seemingly mundane event sparked his interest in pendulum motion, leading him to investigate the principles of oscillation. Galileo's observations contradicted the prevailing Aristotelian view that heavier objects fall faster than lighter ones. This experience marked the beginning of his journey as a scientist willing to question established doctrines and seek empirical evidence. Galileo eventually left the University of Pisa without completing his medical degree, but this decision did not deter his intellectual pursuits. He returned to Florence, where he began studying mathematics under the guidance of Ostilio Ricci, a court mathematician. Ricci's mentorship was instrumental in shaping Galileo's understanding of geometry and mechanics. These studies solidified Galileo's foundation in mathematics, which he would later use to revolutionize the study of motion and astronomy. During this period, Galileo also immersed himself in the works of classical thinkers such as Archimedes and Euclid. Their writings, particularly Archimedes' emphasis on empirical experimentation, profoundly influenced Galileo's scientific methodology. Unlike many of his contemporaries, Galileo sought to blend theoretical reasoning with practical experimentation, laying the groundwork for the scientific method. By the late 1580s, Galileo began to make a name for himself as a teacher and scholar. He secured a position teaching mathematics in Florence and later in Siena, gaining a reputation for his dynamic and engaging lectures. However, his unorthodox ideas and challenges to Aristotelian physics often placed him at odds with more traditional scholars. This tension would become a recurring theme throughout his career. In 1589, Galileo returned to the University of Pisa as a professor of mathematics. It was here that he conducted some of his earliest experiments on motion, famously demonstrating the fall of objects from the Leaning Tower of Pisa. Although the anecdote of the tower experiment may be apocryphal, it symbolizes Galileo's commitment to challenging established notions through empirical observation. Galileo's growing reputation as a mathematician and physicist eventually earned him a prestigious appointment at the University of Padua in 1592. During his tenure, he expanded his research into mechanics, astronomy, and engineering. This period marked the beginning of Galileo's most productive years, as he honed his skills in experimentation and theoretical analysis. In summary, Galileo's early life and education were marked by a relentless curiosity and a willingness to diverge from traditional paths. Despite familial expectations and societal constraints, he pursued his passion for understanding the natural world. These formative years not only equipped Galileo with the tools necessary for his groundbreaking discoveries, but also revealed the characteristics that would define his career: intellectual courage, a commitment to empirical evidence, and an unyielding desire to uncover the truth. The Renaissance, spanning roughly from the 14th to the 17th century, was a period of profound cultural, intellectual, and scientific transformation in Europe, characterized by a revival of classical learning, humanism, and a newfound emphasis on individual inquiry. This era provided the fertile intellectual soil in which Galileo Galilei's genius could flourish. Understanding the Renaissance context is crucial to appreciating Galileo's work, as it was both a product of and a catalyst for this transformative period. At its core, the Renaissance was about rediscovering and reinterpreting the knowledge of ancient civilizations, particularly those of Greece and Rome. Thinkers like Plato, Aristotle, and Archimedes were revisited with renewed vigor, inspiring a departure from medieval scholasticism and a movement toward more empirical and critical methods of inquiry. Galileo's education and scientific pursuits were deeply influenced by this cultural revival. The Renaissance spirit of questioning established authority and seeking answers through observation resonated strongly with his natural curiosity. Humanism, a hallmark of the Renaissance, emphasized the potential and value of individual achievement. It celebrated human creativity and placed a premium on critical thinking. Galileo, as a true Renaissance man, embodied these ideals. He challenged the dogmatic adherence to Aristotelian physics that dominated medieval thought, insisting that knowledge should be grounded in evidence and experimentation rather than tradition. His ability to blend mathematical precision with experimental observation exemplified the humanist emphasis on integrating diverse disciplines. The Renaissance also saw the development of technologies that would transform the way people understood the world. The printing press, invented by Johannes Gutenberg in the mid-15th century, played a critical role in disseminating new ideas. This technological advancement allowed Galileo's works, including his revolutionary Sidereus Nuncius, to reach a wide audience, fueling intellectual debates across Europe. The spread of Renaissance ideals, facilitated by the printing press, created a receptive environment for Galileo's groundbreaking discoveries. Furthermore, the Renaissance emphasis on artistic innovation paralleled advancements in science. Artists like Leonardo da Vinci and Michelangelo were not only masters of their craft, but also pioneers in studying anatomy, perspective, and engineering. Galileo shared this interdisciplinary approach, viewing science as interconnected with art and philosophy. His sketches of celestial observations, including the surface of the moon, were as much artistic as they were scientific, reflecting the Renaissance ideal of harmonizing aesthetics with inquiry. Galileo's relationship with the Renaissance's cultural milieu also extended to its political and social structures. Renaissance Italy was a patchwork of city-states, each with its own patronage systems. Wealthy patrons, such as the Medici family in Florence, supported artists, scientists, and thinkers, fostering an environment of intellectual competition and innovation. Galileo benefited from this system, securing patronage that enabled him to conduct his research and publish his findings. The Medici, in particular, played a pivotal role in Galileo's career, as he named Jupiter's moons after them, strengthening his ties with this influential family. The Renaissance also redefined humanity's relationship with the cosmos, a shift in perspective that Galileo both contributed to and benefited from. The era's renewed interest in astronomy, spurred by figures like Copernicus, reflected a broader willingness to question long-held beliefs about the universe. Galileo's embrace of the Copernican heliocentric model, which placed the sun at the center of the solar system, was emblematic of this intellectual shift. By building on the work of his predecessors and applying the tools of Renaissance innovation, Galileo fundamentally altered the trajectory of astronomy. However, the Renaissance was not without its contradictions. While it celebrated intellectual freedom, it existed within the confines of religious orthodoxy and political power. The Catholic Church, a dominant force during this period, maintained strict control over the dissemination of ideas. Galileo's eventual conflict with the Church highlights the tension between the Renaissance ideals of inquiry and the institutional resistance to change. This dichotomy underscores the challenges Galileo faced as a thinker navigating the evolving intellectual landscape. Galileo's life and work also reflected the Renaissance's pragmatic turn toward understanding nature to improve human life. The era saw the rise of applied sciences, where knowledge was used to solve real-world problems. Galileo's inventions, such as the improved telescope and his contributions to mechanics, were practical tools that demonstrated the utility of scientific inquiry. His ability to apply theoretical principles to tangible innovations exemplified the Renaissance drive to merge thought with action. In conclusion, the Renaissance was more than just the historical backdrop for Galileo's life. It was the crucible in which his ideas were forged. The era's emphasis on rediscovery, individualism, and interdisciplinary inquiry shaped Galileo's approach to science and positioned him as a transformative figure. At the same time, his work embodied the Renaissance spirit, advancing the ideals of empirical evidence, critical thinking, and human creativity. As the chapters of Galileo's life unfold, his story reveals how he both shaped and was shaped by this remarkable period of intellectual awakening. One of Galileo Galilei's most enduring contributions to science lies in his groundbreaking work on mechanics and motion. At a time when Aristotelian physics dominated, positing that objects moved according to their nature and that heavier objects fell faster than lighter ones, Galileo challenged these ideas with rigorous experimentation and mathematical reasoning. His work on motion not only laid the foundation for classical mechanics, but also transformed the way scientists approach the study of natural phenomena. Galileo's exploration of motion began with a simple yet revolutionary premise. Nature could be understood through mathematics. Unlike his contemporaries, who often relied on qualitative descriptions and philosophical speculation, Galileo sought precise, quantitative measurements to explain the behavior of objects. This approach marked a significant departure from Aristotelian thought, which emphasized intrinsic qualities over measurable properties. Galileo's insistence on testing hypotheses through controlled experiments would come to define the scientific method. One of Galileo's most famous investigations involved the study of falling objects. According to Aristotelian physics, heavier objects were believed to fall faster than lighter ones due to their greater natural motion. Galileo, however, questioned this assumption and conducted experiments to test it. Though the story of him dropping objects from the Leaning Tower of Pisa is likely apocryphal, Galileo's experiments with inclined planes provided definitive evidence that objects of different masses fall at the same rate in the absence of air resistance. He concluded that the speed of a falling object depends on time rather than weight, a finding that contradicted centuries of Aristotelian doctrine. Galileo also introduced the concept of acceleration, describing how the velocity of a falling object increases uniformly over time. This idea was revolutionary because it challenged the notion that motion required a continuous application of force. Through careful measurements, Galileo demonstrated that the distance an object falls is proportional to the square of the time it has been falling. This relationship, now expressed as is proportional to 2, d is proportional to t, 2, became a cornerstone of kinematics and classical mechanics. In addition to his work on free fall, Galileo explored the concept of inertia. He rejected Aristotle's claim that objects naturally come to rest without an external force. Instead, Galileo proposed that an object in motion will continue to move at a constant velocity unless acted upon by an external force, a principle later formalized as Newton's first law of motion. This insight was a fundamental shift in understanding motion and laid the groundwork for the development of modern physics. Galileo's investigations extended to projectile motion, where he combined his studies of linear and parabolic trajectories. Using experiments and mathematical analysis, he demonstrated that projectiles follow a curved, parabolic path when influenced by gravity and an initial horizontal velocity. This finding was not only crucial for understanding ballistics, but also underscored the unifying principles of motion, showing that celestial and terrestrial phenomena were governed by the same physical laws. Galileo's mechanical innovations were not limited to theoretical advancements. He designed and built devices to aid his experiments, including inclined planes, pendulums, and water clocks. These tools allowed him to measure time and motion with unprecedented precision. His pendulum studies, for example, revealed that the period of a pendulum depends only on its length and not on its mass or amplitude, a discovery that later influenced the development of timekeeping technology. The implications of Galileo's work on mechanics extended far beyond his own time. By demonstrating that natural phenomena could be described using universal principles, Galileo broke down the artificial divide between the heavens and the earth. His findings provided the empirical basis for Isaac Newton's laws of motion and universal gravitation, which unified the physical sciences under a single framework. Galileo's insistence on experimentation and mathematical rigor also marked a turning point in the history of science. His methods shifted the focus from speculative philosophy to empirical observation, emphasizing the importance of measurable evidence. This approach not only advanced the study of mechanics, but also set a standard for scientific inquiry that remains in place today. In conclusion, Galileo's work on mechanics and motion represents a monumental shift in our understanding of the physical world. By challenging Aristotelian physics and introducing concepts such as acceleration, inertia, and parabolic motion, he laid the groundwork for modern science. His commitment to experimentation and mathematical analysis transformed mechanics from a field of abstract speculation into a disciplined, empirical science. Galileo's legacy in this domain is not only a testament to his intellectual courage, but also a foundation upon which centuries of scientific progress have been built. Galileo Galilei's contributions to astronomy revolutionized humanity's understanding of the cosmos and marked a pivotal turning point in scientific history. Using an instrument of his own design, an improved version of the telescope, Galileo made observations that challenged centuries of conventional wisdom. His discoveries, meticulously documented and disseminated, not only advanced the field of astronomy, but also questioned humanity's place in the universe. Before Galileo's time, astronomy was dominated by the geocentric model of the universe, which placed Earth at its center. This view, rooted in Aristotelian philosophy and Ptolemaic astronomy, aligned with the theological teachings of the Catholic Church. While Nicholas Copernicus had proposed a heliocentric model in the 16th century, this idea was met with skepticism and resistance. Galileo's work would provide critical observational evidence to support the Copernican model, setting the stage for a scientific revolution. Galileo's entry into astronomy began with his improvement of the telescope in 1609. Although telescopes had been invented a few years earlier in the Netherlands, Galileo enhanced their design to achieve significantly greater magnification. His version could magnify objects up to 20 times, a remarkable advancement for the time. Armed with this instrument, Galileo began a systematic study of the night sky, recording his findings with precision and clarity. One of Galileo's first major discoveries was the uneven, cratered surface of the moon. Contrary to the prevailing belief that celestial bodies were smooth, perfect spheres, Galileo observed mountains and valleys on the moon, similar to those on Earth. This observation challenged the Aristotelian notion of celestial perfection and suggested that the moon was a dynamic, physical body, much like our own planet. Galileo's detailed sketches of the lunar surface, published in his 1610 work Sidereus Nuncius, The Starry Messenger, captivated his contemporaries and marked a departure from traditional cosmology. Galileo's telescope also revealed a multitude of stars previously invisible to the naked eye. His observations of the Milky Way demonstrated that it was not a uniform haze, but a dense collection of countless stars. This finding expanded the known boundaries of the universe and emphasized the vastness and complexity of the cosmos. Galileo's work in this area underscored the importance of observational tools in advancing scientific knowledge. Perhaps Galileo's most famous astronomical discovery was the identification of 4 moons orbiting Jupiter, which he first observed in January 1610. These moons, later named Io, Europa, Ganymede, and Callisto, were the first celestial bodies discovered to orbit a planet other than Earth. Their existence provided direct evidence against the geocentric model, as it demonstrated that not all celestial objects revolved around the Earth. Galileo's naming of these moons as the Medicean stars in honor of the Medici family was a strategic move to secure patronage and protect his work. Another critical observation came when Galileo turned his telescope to Venus. He discovered that Venus exhibited phases similar to those of the Moon, a phenomenon that could only be explained if Venus orbited the Sun. This finding provided strong evidence in favor of the heliocentric model and further undermined the geocentric view. Galileo's observations of the Sun also revealed sunspots, irregularities on its surface that contradicted the notion of celestial immutability. He meticulously documented the movement of these sunspots, concluding that the Sun rotated on its axis. Galileo's discoveries were not without controversy. His observations directly challenged the Aristotelian and Ptolemaic systems, which were deeply entrenched in both scientific and religious thought. By demonstrating that celestial bodies were imperfect and that Earth was not the center of all motion, Galileo's findings posed a profound challenge to established doctrines. The publication of Sidereus Nuncius and subsequent works sparked widespread debate among scholars and clergy alike. Despite resistance, Galileo's work had an immediate and transformative impact on astronomy. His use of the telescope demonstrated the power of technology in advancing scientific inquiry. By relying on direct observation and meticulous documentation, Galileo set a new standard for empirical research. His willingness to question established beliefs and seek evidence in nature exemplified the emerging scientific ethos of the Renaissance. In conclusion, Galileo's astronomical discoveries, made possible by his innovative use of the telescope, redefined humanity's understanding of the universe. From the craters of the Moon to the moons of Jupiter and the phases of Venus, his observations challenged long-held beliefs and provided compelling evidence for the heliocentric model. Galileo's contributions to astronomy not only advanced the field, but also embodied the spirit of inquiry and innovation that defines modern science. His work continues to inspire and remind us of the power of observation to unlock the mysteries of the cosmos. Galileo Galilei's endorsement of the heliocentric model, which proposed that the Sun rather than the Earth was at the center of the universe, marked a defining moment in his career and the history of science. While his observations provided critical evidence for the Copernican system, this revolutionary idea brought Galileo into direct conflict with the Catholic Church. The ensuing controversy highlights the tension between scientific innovation and institutional authority, a struggle that has echoed through the centuries. The heliocentric model, initially proposed by Nicholas Copernicus in his 1543 work De Revolutionibus Orbium Coelestium, challenged the long-standing geocentric view upheld by Aristotelian physics and Ptolemaic astronomy. This model aligned with the theological teachings of the Catholic Church, which emphasized Earth's central place in the universe as reflective of humanity's unique role in creation. By contrast, the Copernican model repositioned Earth as just another planet orbiting the Sun, a concept that fundamentally altered humanity's perceived place in the cosmos. Galileo became an ardent supporter of the heliocentric model after making his groundbreaking astronomical discoveries in the early 17th century. Observations such as the phases of Venus and the moons of Jupiter provided empirical evidence that contradicted the geocentric model and supported Copernicus' theory. Galileo's ability to substantiate these claims through precise measurements and rigorous analysis strengthened his case, but it also brought his work under scrutiny from religious authorities. In 1616, the Catholic Church formally condemned the heliocentric model as heretical, arguing that it contradicted biblical passages suggesting that the Earth was immovable and at the center of the universe. The Inquisition placed Copernicus' works on the index of forbidden books and warned Galileo to refrain from advocating for heliocentrism. While Galileo initially complied with this directive, he remained convinced of the model's validity and continued his research and correspondence on the subject. Galileo's relationship with the Church was complicated by his personal faith and his belief that science and religion could coexist. He argued that the Bible was not intended as a scientific text, and that its passages should be interpreted metaphorically when they appeared to conflict with observed reality. In his famous letter to Grand Duchess Christina of Tuscany, Galileo articulated the view that nature, as God's creation, revealed divine truth through observation and reason. This stance placed him at odds with church authorities, who maintained that theological interpretations took precedence over empirical findings. The tension between Galileo and the Church reached a breaking point with the publication of his 1632 book, Dialogue Concerning the Two Chief World Systems. Presented as a debate between proponents of the heliocentric and geocentric models, the book was a masterwork of scientific reasoning and rhetorical skill. However, its portrayal of the geocentric position, represented by a character named Simplicio, was seen as a thinly veiled critique of the Church's stance. This perceived insult, coupled with Galileo's advocacy for heliocentrism, provoked a strong reaction from Church authorities. In 1633, Galileo was summoned to Rome to face trial by the Inquisition. Accused of heresy for promoting the heliocentric model, Galileo was subjected to intense interrogation and threatened with torture. Ultimately, he was forced to recant his views publicly and was sentenced to house arrest for the remainder of his life. Despite this humiliating ordeal, Galileo continued to work in relative isolation, focusing on other areas of science such as mechanics and kinematics. The trial of Galileo is often seen as a clash between reason and dogma, but the reality is more nuanced. The Church's opposition to heliocentrism was not solely theological. It was also influenced by political and cultural factors. The Counter-Reformation had heightened the Church's sensitivity to challenges to its authority, and Galileo's defiance was perceived as a threat to its institutional power. Additionally, the lack of widespread acceptance of heliocentrism among scientists at the time complicated Galileo's position, as his claims were seen by some as speculative. Despite the personal and professional cost of his conflict with the Church, Galileo's advocacy for the heliocentric model had a profound and lasting impact. His observations and arguments provided the foundation for the eventual acceptance of the Copernican system, which gained widespread recognition in the decades following his death. The publication of Isaac Newton's Principia Mathematica in 1687, which built on Galileo's work, definitively established the heliocentric model as the correct understanding of the solar system. In hindsight, the Galileo affair underscores the importance of intellectual freedom in the pursuit of knowledge. It serves as a cautionary tale about the dangers of conflating scientific inquiry with ideological or institutional authority. Galileo's courage in challenging deeply entrenched beliefs, despite the personal risks, exemplifies the spirit of scientific exploration and the enduring human quest for truth. In conclusion, Galileo's support for the heliocentric model and his conflict with the Church represent a critical juncture in the history of science and religion. His empirical evidence and intellectual arguments advanced our understanding of the universe while challenging the boundaries of authority and tradition. Though his trial and condemnation were setbacks in his lifetime, Galileo's work ultimately triumphed, reshaping humanity's conception of the cosmos and leaving a legacy of intellectual bravery and perseverance. The final years of Galileo Galilei's life were marked by both personal hardship and remarkable intellectual productivity. Confined to his villa in Arcetri under house arrest following his 1633 trial by the Inquisition, Galileo's circumstances might have seemed bleak. However, this period became one of profound reflection and enduring contribution to the scientific world. Despite his physical isolation and declining health, Galileo continued to explore the frontiers of science, producing work that would solidify his place as one of history's greatest scientific minds. After his trial, Galileo was forbidden from teaching or writing about heliocentrism. The Church's restrictions did not, however, silence his intellectual pursuits. Galileo turned his attention to other scientific questions, including the study of motion, the nature of tides, and the mechanics of materials. These investigations culminated in his final major work, Discourses and Mathematical Demonstrations Relating to Two New Sciences, commonly known as Two New Sciences, published in 1638. This book, often regarded as Galileo's scientific testament, summarized and expanded upon decades of research in physics. Two New Sciences addressed two critical areas: the strength of materials and the motion of objects. In the first part of the book, Galileo analyzed the behavior of structures and materials under stress, laying the groundwork for modern materials science and engineering. He explored concepts such as scaling laws, showing that the strength of a structure is not proportional to its size, a principle with profound implications for architecture and mechanical design. The second part of the book focused on kinematics and dynamics, further advancing the study of motion that had occupied Galileo for much of his career. He refined his earlier ideas about acceleration and inertia, describing the motion of projectiles and the properties of falling bodies with unprecedented mathematical precision. His insights into parabolic motion and uniform acceleration were groundbreaking and provided the foundation for later developments in classical mechanics, particularly by Isaac Newton. Despite his physical confinement, Galileo maintained correspondence with scientists and intellectuals across Europe. His letters reveal a man deeply engaged with the scientific community, offering advice, exchanging ideas, and inspiring others to pursue empirical research. Galileo's reputation as a leading thinker of his time transcended his official condemnation, and his work continued to circulate, albeit sometimes clandestinely, among scholars eager to build upon his discoveries. Galileo's later years were also marked by personal tragedy and physical suffering. He lost his beloved daughter, Maria Celeste, in 1634, a blow that deeply affected him emotionally. His health deteriorated, and he eventually became blind in 1638, likely due to a combination of cataracts and glaucoma. Yet even blindness did not deter Galileo from pursuing his intellectual interests. He dictated much of two new sciences to his students and collaborators, demonstrating his unwavering commitment to the advancement of knowledge. The publication of Two New Sciences was a significant achievement in Galileo's final years. Though it avoided direct discussion of heliocentrism to comply with the Church's restrictions, its innovative content cemented Galileo's legacy as a pioneer of modern physics. The book's influence was immediate and far-reaching, earning praise from figures such as René Descartes and, later, Isaac Newton. It bridged the gap between Renaissance natural philosophy and the emerging discipline of experimental science. Galileo's contributions extended beyond his specific discoveries. He also helped establish the methodology that defines modern science. His emphasis on observation, experimentation, and mathematical analysis set a standard for scientific inquiry. By insisting that nature could be understood through empirical evidence and universal laws, Galileo transformed the way humanity approached the study of the natural world. While Galileo's conflict with the Catholic Church cast a shadow over his later years, his scientific legacy endured. Over time, the Church's stance on Galileo softened, and his contributions to science were eventually recognized. In 1992, more than 350 years after his death, Pope John Paul II formally acknowledged the errors in the Church's treatment of Galileo, underscoring the enduring importance of intellectual freedom. Galileo died on January 8, 1642, at the age of 77, but his ideas continued to shape the course of science. His work laid the foundation for the scientific revolution and inspired generations of scientists to pursue the truth with courage and rigor. Figures like Isaac Newton built upon Galileo's principles, transforming his insights into the comprehensive framework of classical mechanics that would dominate physics for centuries. In conclusion, Galileo's later years were a testament to his resilience and intellectual passion. Despite the constraints of house arrest and his declining health, he produced work of lasting significance, bridging the Renaissance and the modern scientific era. His contributions to mechanics, materials science, and the scientific method solidified his place as a towering figure in history. Galileo's legacy serves as a reminder of the transformative power of curiosity, perseverance, and the pursuit of knowledge, even in the face of adversity. Galileo Galilei's intellectual achievements not only transformed specific fields such as astronomy and mechanics, but also profoundly influenced the broader scientific revolution of the 16th and 17th centuries. By challenging entrenched beliefs, advocating for the use of experimentation, and emphasizing mathematical precision, Galileo laid the groundwork for a systematic approach to understanding the natural world. His ideas reverberated through the scientific community, inspiring subsequent generations of thinkers and solidifying his role as a central figure in the scientific transformation of early modern Europe. The scientific revolution marked a fundamental shift in the way humanity approached knowledge. It was a period when empirical observation, mathematical reasoning, and skepticism of traditional authorities became the cornerstones of scientific inquiry. Galileo's contributions were instrumental in shaping these values. He exemplified the transition from a reliance on inherited wisdom, often rooted in Aristotelian philosophy and medieval scholasticism, to a method that demanded evidence and experimentation. One of Galileo's most significant influences was his application of mathematics to describe natural phenomena. Prior to Galileo, the study of nature often relied on qualitative descriptions rather than quantitative analysis. By using mathematical formulas to explain motion, such as the relationship between distance and time in uniformly accelerated motion, Galileo demonstrated that nature could be understood through precise, universal laws. This approach bridged the gap between philosophy and practical science, laying the groundwork for figures like Isaac Newton, who would build upon Galileo's principles to create the laws of motion and universal gravitation. Galileo's emphasis on experimentation also revolutionized the scientific method. At a time when many scholars relied on deductive reasoning from established principles, Galileo insisted on testing hypotheses through controlled experiments. His work with inclined planes, pendulums, and projectiles exemplified this method. By meticulously documenting his experiments and publishing his results, Galileo set a standard for scientific transparency and reproducibility. These practices became foundational to the modern scientific community and remain central to the way research is conducted today. Moreover, Galileo's astronomical discoveries challenged the traditional, Earth-centered worldview and paved the way for a more accurate understanding of the cosmos. By providing empirical evidence for the heliocentric model, he advanced the Copernican revolution and altered humanity's perception of its place in the universe. While Galileo faced significant resistance for his views, his observations of celestial bodies, such as Jupiter's moons and the phases of Venus, ultimately proved irrefutable. This shift from a geocentric to a heliocentric perspective not only transformed astronomy, but also influenced fields such as navigation, physics, and cosmology. Galileo's influence extended beyond his scientific discoveries to his broader philosophical stance. He championed the idea that nature and scripture could coexist as sources of truth, but that they operated in different domains. While scripture addressed spiritual and moral matters, Galileo argued that nature revealed divine truths through observation and reason. This perspective encouraged a separation between science and theology, enabling the development of science as an independent discipline. This intellectual shift allowed future scientists to explore the natural world without being constrained by religious dogma. The publication of Galileo's works also played a crucial role in disseminating his ideas. Books like Sidereus Nuncius and Dialogue Concerning the Two Chief World Systems reached a wide audience and sparked debates across Europe. While his later works were restricted by the Church, they circulated among scholars, influencing thinkers such as René Descartes, Johannes Kepler, and Robert Hooke. Galileo's ability to communicate complex scientific ideas in an accessible and engaging manner made his work influential far beyond the confines of academia. Galileo's contributions resonated deeply with the intellectual climate of his time, inspiring other pioneers of the scientific revolution. Figures such as Francis Bacon and René Descartes shared Galileo's commitment to empirical methods and skepticism of untested assumptions. Galileo's work provided a model for integrating observation, mathematics, and experimentation, which became the hallmark of modern science. His influence is evident in the subsequent development of physics, astronomy, and engineering, as well as in the broader cultural shift toward rational inquiry. The broader implications of Galileo's influence extended into fields outside of science. By challenging authority and advocating for intellectual freedom, Galileo embodied the spirit of the Renaissance and Enlightenment. His willingness to question established beliefs, even at great personal risk, inspired later movements that sought to expand the boundaries of human knowledge. The legacy of this intellectual courage can be seen in the development of democratic values, free thought, and the pursuit of truth. In conclusion, Galileo's contributions to the scientific revolution were profound and multifaceted. His pioneering use of mathematics, experimentation, and empirical observation transformed the study of nature and set the stage for modern science. Beyond his specific discoveries, Galileo's philosophical approach and intellectual bravery influenced not only his contemporaries, but also the trajectory of Western thought. His legacy endures as a testament to the transformative power of reason, evidence, and the relentless pursuit of knowledge. Galileo Galilei's life and work represent a profound intersection between science, religion, and intellectual authority. His scientific discoveries were groundbreaking, but his unyielding support of the heliocentric model and his public confrontation with the Church led to a lengthy and contentious conflict. This chapter explores the deeper implications of Galileo's struggles with religious and political institutions, the lasting effects on the relationship between science and religion, and the broader cultural impact of his trials. At the heart of Galileo's conflict with the Catholic Church was the clash between empirical evidence and religious doctrine. In the early 17th century, the Church held considerable sway over intellectual and cultural life in Europe, with the Bible and theological interpretation being seen as the ultimate sources of truth. The geocentric model, which placed Earth at the center of the universe, was deeply rooted in biblical readings and the Church's teachings. Thus, Galileo's support of the Copernican heliocentric model, which placed the Sun at the center of the solar system, was perceived not only as a scientific challenge, but as a theological threat. Galileo's 1616 admonition by the Church to refrain from promoting heliocentrism was the beginning of a long and difficult period in his life. Despite the Church's opposition, Galileo continued his research, arguing that the Bible was not a scientific document and that its teachings could not contradict the observable, empirical facts of the natural world. His writings, especially his dialogue concerning the two chief world systems, continued to advocate for the heliocentric theory, which he believed to be the correct model based on his astronomical observations. This defiance led to his infamous trial by the Inquisition in 1633. The trial itself was a dramatic moment in the history of the relationship between science and religion. Galileo was accused of heresy for advocating heliocentrism, and though he was ultimately forced to recant and publicly reject his own findings, the trial and the subsequent punishment of house arrest underscored the Church's resistance to scientific innovation that contradicted its theological doctrines. This episode highlights the tension between reason and authority that has played a significant role in the history of human knowledge. While Galileo was condemned by the Inquisition, his work lived on, and his findings would later be integral to the development of modern science. However, Galileo's conflict with the Church was not just a personal matter. It symbolized a larger philosophical shift. Before Galileo, the dominant intellectual framework for understanding the universe was one that integrated theology with natural philosophy. Scholars like Aristotle and Ptolemy relied on logic and reason, but their theories were ultimately governed by religious assumptions. Galileo's insistence on the primacy of observation and experimentation, rather than dogma, marked a departure from this tradition and laid the foundation for modern scientific methodology. His work emphasized that the natural world could be understood independently of religious or theological dictates, which was a radical shift in intellectual thought. This new approach to science had profound implications for the relationship between science and religion. For centuries, the two were seen as closely intertwined, with religious institutions serving as the final arbiters of truth. Galileo's trial, however, highlighted the dangers of conflating religious doctrine with scientific inquiry. In the aftermath of the trial, science became increasingly separated from religious authority, setting the stage for future scientific inquiry to be based on observation, evidence, and reasoning, rather than theological interpretation. The legacy of Galileo's conflict with the Church thus contributed to the gradual secularization of science and the development of the scientific method as an independent and self-sustaining discipline. Galileo's trial also exposed the limitations of religious authority in the face of empirical evidence. The Church's stance on heliocentrism was not universally accepted, even within religious circles. some theologians, such as the Jesuit astronomer Christoph Clavius, had already acknowledged the mathematical validity of the heliocentric model. However, the Church's resistance was more political than theological. It was rooted in a desire to maintain its power and control over intellectual discourse. As Galileo's findings gained wider acceptance, this conflict between authority and evidence became an important theme in the development of modern science, influencing later thinkers like Isaac Newton, who would base his laws of motion and universal gravitation on empirical observation and mathematical reasoning. The Church's eventual shift in stance toward Galileo further demonstrated the complexity of the relationship between science and religion. After centuries of suppression, the Church formally acknowledged the error in its condemnation of Galileo. In 1992, Pope John Paul II issued a public apology, acknowledging that the Church had made a mistake in its treatment of Galileo and recognizing his contributions to science. This gesture represented not just a re-evaluation of Galileo's case, but also a broader recognition of the changing nature of the relationship between science and religion in the modern world. While the Church's apology came long after Galileo's death, it was a significant moment in the reconciliation of science and religion. It highlighted that despite their apparent opposition, both science and religion could contribute to the search for truth. Science through empirical observation and religion through spiritual insight. In this sense, Galileo's legacy extends beyond the scientific community. It also contributed to an evolving dialogue between faith and reason, one that continues to shape modern thought. The long-term impact of Galileo's work can be seen in the way scientific inquiry has evolved since the early modern period. His insistence on empirical evidence, experimentation, and mathematical reasoning became the foundation for the scientific revolution, influencing disciplines ranging from physics and astronomy to biology and chemistry. Galileo's rejection of untested theories and his embrace of observation as the basis for knowledge helped shape the intellectual landscape of the Enlightenment and beyond, where skepticism, reason, and scientific rigor became core values. In conclusion, Galileo's conflict with the Church was not simply a clash between science and religion, but a pivotal moment in the development of modern thought. His struggles highlighted the tension between intellectual authority and empirical evidence, and his commitment to scientific truth despite religious opposition paved the way for the modern scientific method. While Galileo's trial had significant personal consequences, it also had profound implications for the relationship between science and religion, marking the beginning of a new era in which the pursuit of knowledge was freed from the constraints of theological dogma. His legacy endures not only in the fields of physics, astronomy, and mathematics, but also in the ongoing dialogue between science and faith. Galileo Galilei's contributions to the scientific world have had an enduring impact, both within the scientific community and in broader cultural contexts. His revolutionary ideas about the cosmos, motion, and the scientific method not only reshaped the understanding of the natural world, but also set the stage for the intellectual transformations of the Enlightenment and beyond. Even centuries after his death, Galileo's work continues to influence fields ranging from astronomy and physics to philosophy and the history of science. His legacy is not just confined to the discoveries he made, but also to the broader framework he helped establish for the pursuit of knowledge. At the core of Galileo's enduring legacy is his role in transforming the scientific method. Before him, intellectual inquiry often relied on philosophical speculation and theological doctrines. Galileo, however, emphasized the importance of empirical observation, experimentation, and mathematical analysis. This approach gave rise to a new way of engaging with the natural world, one based on evidence rather than authority. Galileo's insistence that knowledge should be derived from observation and experimentation became the hallmark of modern science and remains central to scientific inquiry today. His method, which involved forming hypotheses and testing them through controlled experiments, laid the groundwork for the rigorous, systematic approach that characterizes scientific research. Galileo's contributions to astronomy, particularly his observations of the moons of Jupiter and the phases of Venus, were not only pivotal in proving the heliocentric model, but also in advancing the technology of observational instruments. His improvements to the telescope allowed him to peer deeper into the universe than anyone before him, revealing the complexity and dynamic nature of the cosmos. These observations helped disprove the long-standing geocentric view of the universe, and in doing so, challenged the philosophical and theological foundations of centuries-old beliefs. In this regard, Galileo did not just change astronomy. He reshaped humanity's understanding of its place in the universe. His discoveries opened the door for future astronomers like Johannes Kepler and Isaac Newton to further explore the laws that govern the heavens and the earth. The wider influence of Galileo's scientific work can be seen in the subsequent developments of physics, especially in the area of mechanics. Galileo's study of motion, particularly his experiments with falling bodies and projectiles, led him to formulate the concept of inertia. This principle would become a cornerstone of classical mechanics and would be essential for the later development of Newton's laws of motion. Galileo's pioneering use of mathematical descriptions to explain physical phenomena laid the foundation for the scientific revolution in physics, a revolution that Newton would complete with his laws of motion and universal gravitation. Beyond his scientific discoveries, Galileo's intellectual courage and commitment to truth in the face of persecution left a lasting cultural and philosophical legacy. His defiance of the Church's authority, which condemned him for supporting heliocentrism, exemplified the principle of intellectual freedom and the importance of challenging dogma. In a time when religious and political authorities wielded immense power over intellectual life, Galileo's willingness to stand by his convictions helped pave the way for future thinkers to pursue knowledge without fear of reprisal. His legacy of intellectual independence has influenced not only scientists but also philosophers, writers, and political thinkers who have championed the value of free thought in shaping modern society. In addition to his impact on science, Galileo's work has had a significant influence on the way we think about the relationship between science and religion. The conflict between Galileo and the Catholic Church, while emblematic of a clash between faith and reason, ultimately prompted a re-evaluation of the relationship between the two. Galileo's work encouraged a view of science as a separate domain from religious doctrine, one where inquiry is based on empirical evidence rather than theological interpretation. Although this separation has led to tensions at times, it has also contributed to the flourishing of both science and religion as distinct but complementary ways of understanding the world. The eventual recognition of Galileo's contributions by the Catholic Church in the late 20th century symbolizes this reconciliation and reflects a broader understanding that both science and religion can coexist in a complex and dynamic relationship. Galileo's influence extends beyond the scientific and religious realms and into the philosophical domain. His work helped lay the intellectual foundations for the Enlightenment, a period that saw the rise of reason, individualism, and scientific inquiry as guiding principles. Galileo's emphasis on observation and reason, and his rejection of unquestioned authority, resonated with the Enlightenment thinkers who championed rationality and sought to free humanity from the constraints of superstition and dogma. Figures like René Descartes, John Locke, and Immanuel Kant were influenced by the intellectual climate Galileo helped foster, one that prioritized knowledge based on evidence and logic rather than tradition and revelation. Galileo's legacy also finds expression in the way modern science is practiced. The principles he introduced, empirical observation, mathematical reasoning, and experimental verification, remain at the heart of scientific inquiry. Today, scientists across disciplines follow Galileo's model of developing hypotheses, conducting experiments, and analyzing results in an objective and systematic way. The experimental and observational methods he pioneered are applied not only in physics and astronomy, but also in fields ranging from biology and chemistry to social sciences and economics. In this sense, Galileo's impact is felt not just in the history of science, but also in the very structure of contemporary research. As a symbol of scientific progress, Galileo has also become a figure of resistance against the suppression of knowledge. The story of his trial by the Inquisition and his eventual vindication highlights the ongoing struggle for intellectual freedom. Galileo's ordeal is often invoked in discussions about the importance of protecting scientific inquiry from ideological or political interference. His experience serves as a reminder of the dangers of conflating science with ideology and the need to maintain an environment where truth can be pursued without fear of persecution. The influence of Galileo's work also extends to the cultural and educational spheres. His ideas are central to the curriculum of modern science education, where students are taught the principles of empirical observation, critical thinking, and mathematical modeling. Galileo's contributions to the scientific method and his approach to inquiry continue to shape the way science is taught and practiced across the globe. His legacy has not only shaped the field of science, but has also become a model for intellectual rigor and perseverance, inspiring generations of students, educators, and researchers to pursue knowledge with curiosity and integrity. In conclusion, Galileo Galilei's legacy is vast and multifaceted. His groundbreaking work in astronomy, physics, and the development of the scientific method has laid the foundation for modern science and reshaped humanity's understanding of the natural world. His intellectual courage in the face of persecution and his commitment to the pursuit of truth continue to serve as an inspiration for scientists, philosophers, and thinkers across disciplines. Galileo's influence on science, religion, philosophy, and culture underscores the profound and lasting impact of his work, making him not just a central figure in the history of science, but also a symbol of the transformative power of knowledge, reason, and intellectual freedom.